Oh, yeah, I'm Aaron, and this is Aditya. We're going to be presenting our package today, Piccolo.jl, which is an integrated quantum optimal control stack. So I'm at the Robotics Exploration Lab, also at Carnegie Mellon, and Aditya's in the Schuster Lab, which was at Chicago and is now at Stanford, where we've been testing some of this stuff on hardware. So like many of you guys, I'm sure recently, or some of you guys were recently in a movie theater asking some big questions about life, like where is our civilization headed? What does mortality mean? How can we be forces for good in the world? Of course, I'm referring to Barbie. But I'm not going to answer any of those questions today. I'm going to answer some questions about where is quantum control headed? What does direct optimization mean? And how can we go beyond models and actually run stuff on hardware? So first off, like, where is quantum control right now and where is it headed? So this is actually a device that we started testing on. This is what we'd call a quantum flute, or not really. It's a cavity QED device that was at University of Chicago, where basically the photons live inside of this this like physical device, which is pretty big, and like they basically resonate inside of this. And do you have a question? Oh, sorry. Yes, so this is a device that requires some novel control methods. So we tested on this, but we're not going to get into the results of that. If you want to see that, you can see the paper. So quantum optical control basically revolves around pulse optimization. So we have a model Hamiltonian, which is composed of a drift term, as well as drive terms and a drive pulse. And we're going to optimize over that pulse. So conventionally, what people do is optimize some objective that's just a function of the controls. And this is what is known as indirect optimization, because we're not optimizing over the states, which is what we really want to drive. We're optimizing over the controls. So what this looks like is usually this kind of nasty looking function intentionally, which is 1 minus the fidelity. So this is like the fidelity metric, fidelity objective. And then this nasty looking thing is the rollout from the initial state to like a final state. And we're calculating the fidelity with respect to some goal state, X goal. And I'm in a robotics group, so I use X to represent states and U to represent controls. So what is direct optimization? So we do something called direct collocation, which involves minimizing now an objective that's over the states. So it's over the controls and the states. It's a joint optimization problem over everything. And this allows us to easily write out a more simple objective. We're only concerned about the objective over the final states. But then how do we enforce the dynamics? So the dynamics come in via nonlinear constraints linking time steps, k plus 1 and xk, where like you basically propagate forward the xk with the controls to the next step. So these are applied constraint like time-wise on each step, which is a different formalism, and nonlinear solvers can take advantage of this, which I'll show kind of how that works. In this formalism, you can also apply constraints directly on the states, which is very handy for certain things, which we'll show later. So what this looks like inside of the optimizer is the optimizer is kind of figuring out, this is like a state trajectory. So at a certain like initial point, like you have an xk, and then you're going to propagate the xk forward to the orange point via the propagator. So that might not line up with like xk plus 1. So these brackets indicate like the dynamics violations of those constraints, which intermediately in the optimizer is not going to zero those out initially, but at convergence, these will all be zeroed out. So this is like the direct collocation optimization framework. So what is in direct methods versus indirect methods? So indirect methods, like you have to remain in reality. You have to stay feasible trajectories. You're rolling out. You're never leaving the dynamics manifold. And this isn't great. You might be a little sad about your existence. But like in a direct method, you can escape reality and travel between the infeasible world and the world of feasible solutions. So like I'm going to kind of demonstrate what this looks like with a little diagram where this green region is the space of feasible trajectories. So this is like the whole space of all possible trajectories. The green region is the one where the dynamics are satisfied. So the controls roll out to the states. So we're going to start in this purple smiley face, and we want to get here. And there's like some local minimum that we imagine in between. So like an indirect method is going to take steps, gradient descent steps, inside of the constraint, inside of the feasibility manifold. And it might get stuck in a local minimum and might not converge. A direct method, alternatively, can leave the feasible zone and land back leave the feasible zone and land back in the feasible zone at convergence, which is nice. It can jump around this, avoid local minimum. You can also just start totally outside. You can just initialize random trajectories, random controls, random states, and then end back in the feasible zone. So that's like direct collocation in a nutshell. It's not something I don't think anyone in quantum control does at the moment, pretty much just us. Okay, so then there's our kind of spin on this collocation framework, which is kind of acknowledgement of, since our dynamics are now implicit at each time step, and this dynamics for quantum people is an exponential propagator. So you can approximate, with the way your computer actually calculates an exponential is, I don't know if anyone's read the paper, like 20 ways to calculate the matrix exponential. There's a lot of different ways. One of those is known as the Pade approximant for the matrix exponential, which kind of has a forward term and an inverse term. And these are like polynomials in the matrix polynomials. So in this way, like you can look at this, and this is a nice way to calculate the matrix exponential. In the implicit form, we can simply, instead of doing this costly inversion, we can simply move it over to the other side of the x k plus 1, which allows us to do our dynamics calculations like much more efficiently. And we pre-compute a ton of stuff inside the package. And this is where Julia really came in for handling these nasty Jacobians and Hessians, and everything's nicely handled in this formalism. Okay, so this is all detailed in our paper, Direct Collocation for Quantum Optimal Control, where we show like basically the theory behind this, and we test this on this circuit QED system with like state-of-the-art results. And this is kind of like what a trajectory looks like via a pulse from our solver. So that was pretty much a way to do quantum optimal control with a model Hamiltonian. So what if like we run the pulse on the hardware, and the hardware like gives a result that isn't optimal? There's some model mismatch error. So coming from robotics, there's a nice way to handle this, and this is something called iterative learning control. So what you're seeing here is you're looking up your lap numbers. So this drone is trying to track a figure-8 trajectory. And that you'll see, so lap 31, we're just gonna restart in a second. So lap 1, it's doing a pretty crappy job of tracking this trajectory. And it's like making measurements of its position, its velocity, and it's noticing that it's not doing a great job. And after each loop, it's like computing an update to its controls. So by lap 30, it's pretty much right on the figure-8. So this is an idea called iterative learning control, which there's been like some limited like tests and simulation and stuff. Actually, Andy back there has written a paper on this for a certain case, but we're working more on this in this collocation format too. So in the quantum case, like there's some extra considerations. So we start with nominal controls. We get a nominal control pulse. We run it on an experiment. We measure it, and these measurements are noisy, projective, and very costly. And we don't want to measure the full stakes. That's super costly at every time. And anyway, we make our measurements. We compare them with like the nominal measurements coming out of the solver, and we get some measurement mismatch error. And we're going to use those updates, that error, to compute an update to the pulse using the hardware and our model, which is like kind of different than a reinforcement learning framework where you're not using a model at all. Here we are, and this leads to like sample efficiency improvements and just a better way to probably handle this problem. And so that's going to be demonstrated in code actually in a little bit. Okay, so before I hand it off to Aditya to do a code, I'm going to go over like the Piccolo.jl package, which is a meta package actually that has 3 packages underneath. So it has this package NamedTrajectories, which was birthed out of a lot of pain handling indices for tons of different trajectory components. So this handles that very nicely and efficiently and gives a lot of neat functionality that keeps getting added to as we discover new needs. And then QuantumCollocation is really the workhorse of the collocation framework, which interface with IPOP.jl to do the nonlinear solver. the nonlinear solves underneath. And then also we have QuantumIterativeLearningControl.jl, which just got registered yesterday. We had another package that was registered, but this handles the ILC format, which I didn't get into the math, but we are going to demo it in code. So I'm going to hand it off to Aditya.
All right, yeah, so let's switch to the live code demo now. So let's sort of look at sort of a very simple toy example just to demonstrate how like our whole Piccolo package works. So okay, let's just go ahead and like load everything in first. And so here we're just going to consider a very simple like 2-qubit Hamiltonian in like a rotating frame just to make things simple for us. And so here in the rotating frame, all that's going to be left is this coupling between our 2 qubits, and that's the first term. And then our controls are just going to be these direct drives on the qubit. And so here we've written things in terms of like creation and annihilation operators, but you could also equivalently write them in terms of Pauli operators. And you can think of that coupling as sort of just like a ZZ coupling. But okay, so let's go ahead and build this system. So we've gone ahead and defined our Hamiltonians as well as the different drive terms that we have access to control our system. And so once we've sort of defined the system, we can then pass it to this. We can set up this quantum system object that's just going to store our model of our system and go ahead and build this system. So the task that we would like to consider today is just a C0 gate on our 2-qubit system. So we should tell Julia what a C0 gate is. And so there we go. That's C0 gate. And then okay, let's sort of define a sort of like initial guess for how long our pulse might be. So we're going to say it's 15 nanoseconds long, and we're going to use 100 different knot points in our trajectory, or like 100 different time steps in our trajectory. And so each delta t is around 0.1. And so this is also a bit important because we are going to use like a 4th order Pade approximant. And so you kind of want to, you also have to be a little bit careful about like how big you make your time steps relative to your controls in order for that to, accurately match the actual exponential dynamics. Okay, and then now we're going to say that we have some bounds on our controls, so we can't drive it more than 17.5 megahertz. And then also we want our controls to be somewhat smooth. So we're also going to put a constraint on how big the second derivative of our controls can be. Okay, great. Now that we've sort of set up the problem, we should actually go ahead and and like actually build the problem. And so to do that, we're going to use this unitary smooth pulse problem constructor. And so this is just like a handy like template that is able to build problems for us. But you actually have much more lower level control of the problems if you want. And that sort of functionality comes in through named trajectories as well as some other more detailed ways to construct these problems. But here we're just going to use this unitary smooth pulse problem to build our problem. And the one important thing to note here is that we've put constraints on delta t as well as this time step all equal constraints. So actually what the solver can do in this case is actually a free time problem, which is also especially hard with, it's harder with these indirect methods. But in our case, we're able to satisfy the dynamics, we're able to both adjust the controls, the states, and the time step. And in order to make sure the solver doesn't take advantage of any kind of discretization error, we need to make sure we put some bounds on delta t so that it can't make delta t either too big or too small. And then for convenience, we're going to say that all the time steps need to be equal, just so that we have like a nice sort of evenly spaced trajectory. So now that we've set up this problem, I kind of want to show off some of the features of NamedTrajectories.jl, which came out of this problem of having to index into trajectories if you want to sort of get some component of them. So earlier, like trajectories would be stored as these like matrices or these vectors of vectors. And if you wanted to get the controls, for example, you would need to like make sure you are like being careful about how you're indexing into the trajectory. But now we just have these different names for each of the parts of our trajectory. So the first part is this unitary that's stored as like a real vector. So it's like an isomorphic real vectorized version of our unitary. And then we have these other 3 components, which are the controls, the derivative of the controls, and the second derivative of the controls, and then finally the time step. So now if you want to sort of access any of these components, it's just as simple as sort of calling like traj.a to get the controls. And then here we can now take a look at what the total size of this problem is. So we have 100 time steps, and then so the total problem dimension here is 4,500. And these are like all the different things that the optimizer has control over to solve the problem. Okay, the next nice part about named trajectories is that it makes plotting very easy. So we're going to go ahead and feed it the trajectory. We're going to plot our states, which is this isomorphic unitary, and we're going to plot our controls. And then we're also going to tell it to ignore labels on the states because this is plotting like 32 different elements because it's like a 2-qubit system, and then it's sort of this isomorphic vector. So there are 32 elements when you take the real and the imaginary part. So then that's another factor of 2. And so there are 32 elements in total, and we don't want to plot a 32-element legend. So this is kind of what the matrix elements of the unitary look like, and this is what the controls look like when we first set up the problem. So you can notice here that what we've done is we've chosen a random initial guess for our controls, and then for the unitary, we've set up, we've basically chosen this like geodesic from the identity to our C0 gate, and that is sort of the initial guess that we give it for the unitary. So in practice, you can give it whatever initial guess you want. We just find that this like geodesic initial guess for like unitaries in particular works pretty well. But now you might say, okay, this is kind of hard to see, so maybe I want to like look at some other nice part of this trajectory. So what I've done here is we can use this transformation feature in our plotting function. And so here what it's going to do is it's just going to convert our vectorized unitary to the actual unitary, take the third column, and then look at the populations there. And so now we can, for example, see what the evolution of the 1-0 state looks like under our initial guess. And you can see it goes from 1-0 to 1-1 as it should under the C0 gate. Great, so now that we've set up the problem, we should go ahead and solve it. So this is going to solve the problem. It's going to call IPOpt. And you can see that as this sort of runs, the objective is decreasing. And in the second column is sort of the constraint violations. And you can see that that is also decreasing as this runs. So I let this run for like around 100 iterations. So this should like finish in a few more seconds. But yeah, essentially, this is sort of how you set up the problem and then let it run. Yeah, so this should so okay, it's terminated here. If we ran it for more iterations, it would reach convergence. But in the interest of time, I just sort of capped it at a 100 iterations. Okay, so now if we look at the fidelity of our output, we see that we sort of have 5 nines of fidelity. And this fidelity function is actually taking the controls that are output by the solver, and it's then rolling out these controls and then taking the fidelity. So it's not just taking the final state from the trajectory and like looking at what that fidelity is, because that may in general be slightly different from the actual fidelity when you roll out under the matrix exponential. Great. Okay, so now that we have this, let's go ahead and look at what our solution looks like. So you can see it's different from the geodesic solution. And then here is our actual pulse for achieving the C0 gate. And then again, let's look at what the evolution of the 1-0 state looks like. So under our pulse, we see that the 1-0 state goes to the 1-1 state. So that's all. That's good. Okay, so now we have this like nice nominal solution for our C0 gate, but then maybe you want to ask like, okay, how fast can we actually do this C0 gate without sacrificing fidelity? And so this is another place where this whole like nonlinear program framework comes in useful, because we can then put a constraint that tells us that the fidelity of our final unitary cannot drop below some minimum fidelity. So let's say we want to sort of maintain 4 nines of fidelity. We can go ahead and build that enforce that constraint, and then use this unitary minimum time problem feature to sort of very easily build this minimum time problem. And so now, once we've built this minimum time problem, we can go ahead and solve it. And so what's happened here is that in this minimum time problem, we've added a term to our objective that basically looks like the sum of all our time steps. And so that's basically putting a penalty on the total length of the pulse. And so using this framework, we're able to both say, like, OK, we don't want to sacrifice fidelity, and we also want to go as fast as possible. And so once we run that, and then now look at the solution, we see, OK, we maintain 4 nines of fidelity. And let me go ahead and plot this really quickly. And so once we look at the solution, we can see that it's faster than before, and also it's a lot more bang-bang than it used to be. So it's sort of maxing out the control bounds as much as it can over the course of the trajectory. Great. OK, and then finally, if we want to just check how much we improved, we see that from our nominal solution, we've sort of improved by 1.3 nanoseconds, or like around maybe like 10% improvement in our minimum time solution. Usually this is more useful for like cavity QED systems. We're able to get like much bigger improvements using minimum time, but this is like a very simple toy problem with 2 qubits, so we don't see too much of a improvement necessarily. Okay, now the next really exciting thing is that suppose that now we've gone and we've like gotten our minimum time pulse, then we go try it on the hardware, and it doesn't perform as well because there's some mismatch between our model and our actual system. So here we're just going to consider this toy example where there is mismatch of this form. So there are these Pauli operators in our Hamiltonian that we didn't know about, and so this is going to cause our pulse to not actually do the C0 gate as perfectly as it says it's going to do it in simulation. So let's go ahead and sort of just build this error Hamiltonian. And then let's go ahead and build these 4 states. So what we're going to do here is we're going we're going to try our control pulse on this system with these error terms, and then we're going to make 4 different measurements. The 4 measurements are just going to be fidelity measurements on each of these 4 basis states, so on GG, GE, EG, and EE. And then using just these 4 numbers, we will be able to actually improve the pulse using iterative learning control. Great. So let's define the measurement. So this measurement is just the fidelity of the state at the end of the trajectory. And then we're going to go ahead and build this simulation experiment that uses this Hamiltonian that has some errors that were not in our original model. OK, so now that we've done that, let's tell it that we want to track this reference trajectory, which was our minimum time trajectory. So we're going to go ahead and do that. And you can see now that because of the errors that are in our new Hamiltonian, the fidelity has decreased to like 98.9% from like 99.99%. So that seems like a pretty significant hit to our fidelity. So we'd like to try to fix that. So we're going to go ahead and set up this ILC problem and then go ahead and solve it. And so this thing converges very, very quickly in like 5 iterations. And now if we go ahead and take a look at what happened, we can see that the fidelity of our pulse has improved from 98.9 to 99.5 using just fidelity measurements. So these are like very restrictive measurements that don't like have that much information about the state. In practice, you can also use like much more detailed measurements. Like you can do like full state tomography, and in that case, you can get much better improvements to your final fidelity. But those are of course very costly. So the fact that you can sort of get away with just making fidelity measurements is pretty cool. And so if we want to now see like what actually happened to the pulse when we ran ILC, it looks like this. So you can see it converges very, very quickly after just 3 or 4 iterations, and you can see it kind of like shrinks the pulse and like introduces these like small kinks in the pulse to make up for some of the modeling error that used to be there from these extra Pauli terms in our Hamiltonian. Okay, and then we can just check again like what the infidelity is. We see it sort of goes down by a factor of 2, and then yeah, this one will just give us the % change, and so we've improved by a factor of 2 here. Okay, great. So that's sort of it for the live code demo. Before we end, I just want to talk about some future directions for PICO. So the first thing is that we can actually get some we can get some performance improvements from using a slightly more convenient way to represent this like isomorphic vectorization of the unitaries. So this like more convenient way means that the Jacobians and the Hessians have a slightly nicer structure, and we've sort of tested this, and it's sort of given us sort of 10% improvements in speed and memory when calculating the dynamics Jacobians and Hessians. And so actually this is not really future work because we already implemented it, but we haven't really pushed it into main yet. So but it'll be there soon. The next thing is this memorization of the dynamics Jacobians and Hessians. So there's actually a lot of repeated structure in our dynamics Jacobians and Hessians. And so if we can sort of memorize some of those computations, we should be able to get significant speed up, since like a lot of the bottleneck is in calculating these 3 things before we sort of feed this information to IPOpt. And then the next thing is that like higher order Pade integrators become kind of challenging to like analytically derive, but we spent some work sort of figuring out how to do this, like figuring out how to sort of hand code these derivatives. Currently, if you want to use higher order Pade integrators, it's going to just auto diff it, but we actually have a way to hard code them, so we're going to implement that soon as well. And that should also give us some speed ups for those harder problems. And then finally, Piccolo or quantum collocation is going to have support for nonlinear controls. So what I mean by that is maybe in your Hamiltonian, you have a term that depends on a control alpha, but then you also have a term that depends on like alpha squared. And so it's going to soon have support for nonlinear controls as well. And yeah, that is sort of the end of the talk. Thank you.
OK, let's open up to questions.
I might missed this in the notebook, but what's the qubit model you guys have? What's the qubit frequency, and are they anharmonic?
So yeah, it's just like this toy model. We're in the rotating frame, so the qubit frequency is like rotated out. So the only thing here that's sort of remaining is like this coupling, which is like 100 megahertz.
But are they anharmonic?
Oh yeah, so yeah, it's just like a 2-level model. So it's like super. Okay. It's like a toy example that we put in the notebook just to sort of demonstrate the different parts of the whole like Piccolo stack. But yeah, like in general, there are a lot more complicated problems that we solve with this whole this stuff. For example, like preparing like Fock states in a cavity, or other more complicated things like binomial codes and stuff like that, or even just like bigger systems. Yeah, and you can also we've also like tried stuff like modeling higher levels of a transmon or something. And yeah,
Okay,
that's all fine. This is just like a toy example.
Okay, but in general, it works for higher levels?
Yep. Yeah, the nice thing about Pico QuantumCollocation.jl is that like, yeah, for the higher level stuff, they're like nice ways to like put like L1 costs on like populating higher levels, and then that turns out to be really nice if you want to sort of prevent leakage into higher subspaces. Yeah.
Other questions?
Yeah, just a quick one for me. So the method you're using for the time evolution looks like, to me, it sounds very familiar to the parallel algorithm to an extent. Have you heard about this one, first of all? And then second of all, if you know about it, could you maybe comment on if there's some differences and on? If not,
What was it called again?
parallel.
Parallel?
Essentially, you shoot multiple trajectories starting at different time points, and then you try to match them up.
So I have not looked at that. This is in particular not a shooting method, is like the main point of this, is like at any one time, like pretty much all these dynamic calls are actually called in parallel. Like they're all multi-threaded. So
Yes.
like you do not need to do anything shooting wise between it, which is one of the advantages.
In parallel, also each branch is evolved at the same time, and then you match up later.
Or like each branch, like I'm talking about between each time point, between each not point. So this is like the controls lingo. Between each not point, like that dynamics constraint is like each of these is given to the solver, and the solver evaluates them in parallel. Is that okay? I've not looked at this, so
Yeah, I would be interested to see if there's maybe some overlap. Yeah, but thanks for the comment.
over.
And we have a minute or two still left. If there are no other questions, let's please thank the speakers again.
Thank you guys.